Physics Form 4, Chapter 3, Gravitation, 3.3, Man-made satellites. Man-made satellites. Man-made. Okay. The other one is what made? What made? Is, you know? God made. God made. God made. Man made. Okay. This man here not refer to a man, a male person. No. This man here refer to human. Human touch things. Okay. Create something. Is what we call man-made satellites. If God made satellites, then what will it be? It is a the moon. The moon is satellites that God made for our planet. That is Earth. Okay, that is the original satellite. The first and original. This is man-made satellites. Okay, you know what? These man-made satellites nowadays, more than, if you watch the video that I sent you a link, have you watched it? How many this satellite man-made is up there, orbit all around our orbit, Earth orbit. Okay, there are more than 10,000, is it? 10,000, wow. So many. So next time they send a rocket, so they need to slow down to observe either they can pass through or not, because if they don't really careful, they will collide. They will hit the satellite up there. So many. And you know what? We also got junks. So many junks up there. So many junks flying all around the orbit. So many junks. We need to do something about that too. Okay. Let's begin. Orbit of satellite. Figure on the right shows the International Space Station, abbreviation ISS, and MISAT satellite. MISAT, here it is MISAT, and here it is ISS. Okay, you maybe look this small. What do you think this size might be? What do you think this size might be? Is it big or small? Is this satellite big or small?
Big.
Big. That you can walk. It is very big that you can walk up there. And this is you. Can you see that? This is you. Okay. That is you. Even smaller than this. To tell you that this is big actually. They can walk. They can go inside there. Inside this hub, you can see this kind of cylinder things. Okay. Moving along. ISS can be seen from the Earth because of its large size. Okay, can be seen from the Earth, you know. But you need to get a binocular to see this even more clear. because of its large size and orbits at a height of 408 kilometer. 408 kilometer only. How long does it take from this Berlin to Johor? Does somebody know? What is the distance from this Kedah to Johor? Is it about 7 to 800 kilometer? Correct? 7 to 800 kilometer. But so you know, between you and this satellite is only a half, a half distance, 400 kilometer. Okay. MISAT satellite is difficult to be seen because of its small size. Okay, this one is in small size only, about a bit of a car, or two, maybe, and orbits at a height of 35,000 kilometer. Okay, 35,000 kilometer. Okay, they sent it to go further than our Earth. This further, 35,000 kilometer. Satellites move in orbits at specific heights and suitable linear speed. Okay. Notice this. Notice this. Suitable linear speed. Okay, speed. They use the term speed, not acceleration. You know. Because you already know that we have two types of motion. Remember, the first one is velocity or speed, and the second one is acceleration. So hope you can imagine this, that all the satellites moving in what types of motion, type of speed. Okay, speed. Formula for centripetal force and Newton's universal law of gravitation that you know already, okay, are used to establish and determine the linear speed of satellites. Okay, to find the value, to create a formula to find the speed. Okay, by using this combination of these two formula. Figure under shows the orbit of a satellite around the Earth. Here it is, orbit our Earth. Okay, with this radius, with this centripetal force F, with this linear speed V, with this mass of the satellite. Okay, a satellite moving in a circular orbit around the Earth. Circular. Okay, the Earth experiences centripetal force, which is gravitational force. Okay, gravitational force between satellite and the Earth. Okay, that we know the general equation for to find the gravitational force of the Earth is this. Not only the Earth, but whatever the planet it is. Okay, we use this. But you know what? Let's take this moment to go back to this formula. So you will have a better it will clear our whatever that it is not clear lah. So let's go back to this, where we get this F equal to what? FF. Where is it? Oh, here it is, huh? Here it is. And this is what this is what known as Newton's universal law of gravitation. Okay. Between two bodies, because we got 2m, 2m. Okay. So the idea is, if you want to find the attraction between them, the force between two body, then we can use this formula. Okay. So in this case, between two bodies, satellite and Earth. And then we learned about centripetal force on satellite. Okay, centripetal force. So here it is, the formula. Do you still remember the activity for to find the centripetal force? The simple one: use a straw and a string and some load. Do you remember this one? Okay. Okay, a simple activity to find the value of V and the other component. Okay, moving along now. Now in this case, okay, this F here actually the same as this F. Okay, do you understand? This F here is the same as this F. This is when we going to derive another equation to so we'll have the new formula to find V, to find speed. Okay, so we're going to put this component to left side and put this all the component to right side, and then you know what you need to do. You're going to cancel whatever that you can cancel, okay, and whatever that is left, okay, and V here going to be the subject, and the other all the component going to be on the right side. So here it is, how to find the speed. The speed of second body orbit the first body. In this case, to find the speed of this satellite rotate or circle or orbit this body, that is Earth. So you want to write this down on your notebook, your collection of formula. Okay, V equal to square root gravitational constant G, a constant gravitational constant multiply big mass. Big mass here refer to the highest in mass between two, the highest one. In this case, of course, the highest mass is the Earth. Okay, big M. The smallest, the lower mass is for satellite, lower M. Okay, so we see in to find the linear speed here, we doesn't require we do not need to know the mass of the whatever that orbit this Earth. Why? Because here got no small m, got no small m. Okay, the only thing that we need is, in terms of mass, is the mass of the Earth itself. and of course the radius. Okay, you know this radius refer to what? From where to where? From the center to the orbit. Here are some information. Let's read this. Astronautical engineering involves the field of physics on orbital mechanics, outer space environment, guidance and control of height, telecommunications, aerospace structure and rocket propulsion. Okay, does somebody want to your ambition want to be this? Okay, you can keep going with this, astronautical engineering. Okay, but there is a little problem. We got no NASA. Okay, we got no NASA in Malaysia. Need to establish one. As GM is constant, yeah, we know that the G and M is can never be changed. The value is constant. So it is like we can memorize whatever the thing that is constant. Linear speed of the satellites only depends on the radius. Only depends on the radius. Let's go back. So since whatever up there is constant, so the idea is the speed of the satellite is depend only to this r, the radius. Okay, whatever the speed of the satellite refer to this r only. Okay, if r change, the speed change. Okay, we cannot say the speed will change if the m and g, capital G, change. Why? It can never be this mass of earth change. The mass of earth remain the same, correct? And so does G, the gravitational constant cannot change. It is constant. So the only thing that can affect the value of V is R. Okay, you understand this one? This mathematics here tell us, confirm us that only R can change. Where is it? Linear speed of the satellite only depends on the radius of its orbit. Very true. If a satellite is at height h above the surface of the earth, then we know already. We need to plus the radius from center to the surface of the earth lah. Okay, represented by this capital R here. Okay, therefore, okay, this R here actually we need to combine. Okay, small r here stand for this capital R plus H. Okay, so R supposed to be like this, from center to this orbit. So this is why we got two types of R. So here it is from center to the earth, and here it is from surface to the orbit. Okay. Because you know what, the student before you when they come to substitute the value inside this formula, everything is okay, but only they make a mistake on this in this R, on this R. That is, they take only they assume that this is the R from surface to the object, which is wrong. Very wrong. need to include this R too. We add both of them like this. So be careful with it. Oh, sorry. Okay, here we continue here. Man-made satellite can be launched to keep orbiting at specific heights around the Earth at radius of orbit r if the satellite is given linear speed that we derive already. Figure below shows a global positioning system GPS. Okay, satellite at an altitude of 2,200 kilometer, 20,200 kilometer from the Earth. Okay, means this is R, correct? From the Earth. From the Earth. Oh, sorry. This value here refer to H only. Means be careful with that. H only. Okay. This R we know already. The radius of the Earth from center is also a constant. So this is when we need to what? We need to add this R. What is value of R? Why multiply 1,000 meter here to find height? Oh yeah. Since this is not in SI unit, correct? This is kilometer. SI unit is meter. So kilo, we need to convert this kilo to value that we know. If this kilo got 3 0, so we can add 30 at the back. So this is this is where it become like this. And then we need to find this radius of orbit, that is lowercase r. Means that we need to combine, okay, H and R, capital R, and the result is this. And this is when we take this value to substitute in R. Okay, we do the calculation, and then we'll have this answer. What this answer tell us? What this answer tell us? It tell us V. Okay, V is linear speed of satellite motion. Means that, can you imagine how fast this satellite move? Can you imagine this? If you cannot imagine, then let's turn this to whole number so we can see it clearly. So we got 10 cubic. 1 2 3. So it is 3870 meter per second. Oh wow, can you imagine this? If we turn this to kilometer, then it is 3.87. It is almost 4, let's say almost 4 kilometer. 4 kilometer it travel, that takes only 1 second. Wow. Wow, do you understand? Can you imagine this speed?
Yes.
It is like you run out from your home. you get out from your home, then you start running until 4 kilometer. Can you do that in just 1 second? Can you do that?
No.
I can do that. No, nobody can do that. This is way too fast, very fast. Only 1 second, 4 kilometer. Oh wow! You know what? Let's make a little comparison. We know that this here is Baling. Okay, here is Kuala Lumpur. Okay, this distance is 400 kilometer. Let's say almost 400 kilometer lah. Baling to KL. Baling to KL. Okay. So is 1 second can travel 4 kilometer. Then how many times does it take to travel from Baling to KL? Do you understand me? We do the proportion lah, right? 1 second travel 4 kilometer. If 400 kilometer, then how many second? 4 to 400, we multiply with 100. Okay, 100. And so does the denominator under. We need to multiply, to be fair, to multiply the same, 100. Wow, 100 second only. So this satellite can travel from Bali to KL. It takes only 100 seconds. That if we turn this to minute, there is 1 minute and what is the balance? 40. Oh, 40 seconds. Oh wow! Can you imagine the speed? Ah. Okay. You maybe ask me why he need to transfer. Sorry, why he need to travel? Why this GPS need to travel so quick? Sorry, so fast. Why? Does this satellite try to chase something? Why he need? Why they need to travel fast? Why? Any idea? Don't have any idea? Any idea? No? No idea? Why? Try to explain why. Tak tahu? Why they need it need to? Why they NASA that belong to America, they set the speed, the what, to travel that fast? You don't know, huh? Okay. Okay, this is the country which sent this satellite to the orbit, and this is the satellite. Where is my okay? So I stick a needle there at the center of the earth, so it won't move around, but only rotate in this by the center. This is why. If you understand what I mean. Do you understand? Do you understand something? I'm doing like this. Don't you understand something? Because they want this satellite always to be up on their country. We know that this Earth also rotate, correct? This Earth also rotate. Okay, like this, correct? Okay. So if this Earth rotate, we see that this Earth rotates slowly like this, but this satellite need to move even faster than this to catch up this. To catch up this, to be always up on the country. So this is why the idea is the the higher that you'll be from the Earth, the higher the what the higher the speed that you need to do to catch up whatever on the surface of the Earth, like that. See? Oh, this one must travel in high speed than this one. Okay, and this one need to travel in high speed than this one. You got the idea?
Yeah.
Okay,
Yes.
so that is the idea. The what? The more the radius, the higher the speed. To to matching the speed of, to be always on top of the country lah. Now, okay. If this don't catch this, guess what? uh, it will be here at another time, and this satellite going to be up on the other country. Yeah. Okay. How funny it is. Okay. So where are we? Okay, we continue here. 8 8:40, 9:40, 10:10. Okay, 10:10 we finish. Moving along, in a stable orbit, linear speed of satellite is this. Okay, this linear speed is high enough for the satellite to move in a circular orbit around the Earth. Centripetal acceleration is the same as gravitational acceleration. Okay, F equal to F. Different formula, but F refer to same F. If the linear speed of the satellite becomes less than the required linear speed, the satellite will fall to a lower orbit and continue to revolve towards the Earth until it enters the atmosphere. Okay. The movement of the satellite at a high linear speed against air resistance will generate heat and eventually cause the satellite to burn. Okay. After the, you know what? At this position, the satellite doesn't hit the air. And why is that? Because it is vacuum, no air, nothing to be collide in this orbit. Okay, but if the speed is lower than it should be, the satellite will begin to fall to the Earth. Okay, will begin to fall to the Earth, and when it fall, we know that it going to collide with the air inside. Remember, this our atmosphere here filled with um, filled with the air inside here between the surface and uh, the orbit, the atmosphere. So this is, yeah, you guess what? It it will fall also in very high speed, very high speed. So this is when the air resistance also will get higher. The higher the speed, the higher the air resistance to resist the speed, to resist the motion. And the higher the air resistance, the higher the heat generate, and eventually burn. It's going to burn whatever that hit the air. This explains why we can see the meteorite every time meteorite entering our atmosphere. It looks like a spark. We can see them. Why? They burned. They burn. They burn. Okay. The light coming from this burn is when we can see the meteorite. You got the idea? Okay. Meteorite that move in this empty space here in vacuum, we cannot see them. Why? They do not burn. No light emit from them. Okay. Once they enter our atmosphere, then we can start see them, because they collide with air. It looks simple, it looks impossible, but you know what? Even we ourselves, if we collide, if we hit the air with very high speed, we also tend to burn. We also tend to burn. Okay. Geostationary and non-geostationary satellites. Okay, a new term here, geostationary and non-geostationary satellites. What does it mean? Figure below shows two types of satellites orbiting the Earth, which is geostationary satellite and non-geostationary satellite. Study the features of the satellites. Before that, do you know the word stationary? Do you know the word stationary? Stationary means kind of rest, at rest, or doesn't move. Okay, doesn't move. Okay, let's move along. Geostationary satellite in a special orbit named the geostationary or Earth orbit. In a special orbit named the geostationary Earth orbit. Oh wow, we got this orbit that the name is this, the geostationary Earth orbit. Okay, special orbit, special orbit. Got many orbit, but this one is special orbit. Second, moves around the Earth in the same direction as the direction of the Earth rotation on its axis. Okay, as I showed to you earlier, this one, okay, this one, the same direction. Orbital period T equal to 24 hours. That is our what? Our our time taken for this earth to rotate, from this point, let's say, rotate until it back at this point, okay, and so does the thing around it going to rotate with 24 hours too lah, for this geostationary satellite, because they want to keep with the same axis. So this is why they need to preserve the time. This is why they need to go, the more the radius, the more that they need to go in speed, to catch up whatever up there, whatever down there. Okay. What is it? As that is the same as the period of rotation of the Earth. Okay. Always above the same geographical location. Okay. Always above the same geographical location means always up, always up on the whatever country it is lah. Okay, whatever country it is. Okay. Non geostationary satellite, normally in a lower or higher, okay, it can be either lower or higher than that special orbit. Okay, that what we know, it is known as geostationary Earth orbit. Okay. Second, orbital period is shorter or longer than 24 hours. Okay. Shorter when what? Shorter, oh, it doesn't matter, either it is lower or higher. So lower, if lower, it can be shorter or longer. If higher, also it can be shorter or longer than 24 hours. Okay, depend on what speed that they want it to travel. Above different geographical locations at different times. Okay, see, it can change the place lah. Okay, it can be up on any country lah at different times. Okay, it is like this. The non-geostationary kind of move randomly, randomly, wherever they want to go. Okay, but still in the same orbit, still in the same orbit. Okay, it is just their direction. They can move wherever the geographical that they want, they are in certain time lah. Okay, and then we have this activity to gather information on geostationary and non-geostationary satellites. Okay, you Google this yourself lah. Okay, you can find the function. What is the function they create the satellite and get them up there. Okay, and what is their lifespan? Okay, how long will they live lah? How long? Figure 3.37 below shows the comparison between geostationary and non-geostationary satellites, as well as example of the satellites. Okay, here it is. They arrange this in a very good mind map. Okay, very good one. So this special mind map here, we use this special mind map here when we come to compare. Compare mean, what do you understand by compare? We kind of find the whatever the characteristic that shared together between this thing between these types. Okay, they are similar in this. Okay, they both similar in this. Both of them, they orbit the earth, correct? Both of them, they we can find their speed by using this formula. Okay, correct? And both of them, we can find the time taken, the period to complete one orbit. Okay, using this formula. Okay, that is the same thing shared with both of them. Okay, and this is a comparison. Okay, the other one is what we call differentiate. Okay, different between them differentiate. Okay, that only them who have the characteristic respectively. So this geostationary satellite different than the non-geostationary satellite. It can the direction of motion same as the direction of Earth rotation. Okay, the direction the same as the direction of Earth rotation. While this one direction of motion need not be the same as the direction of Earth rotation. Okay, this is how we differentiate between them. Okay, and this one T equal to 24 hours, and this one T is either shorter or longer than 24 hours. This is how you mention T. And then above the same geographical location, above the same, always above the same geographical location. While this one above different geographical location. Okay, it can be on top of any country lah. This one communication satellite. Okay, used as a communication satellite. Okay, while this one for Earth imaging. Okay, Earth imaging. So this is when this is why they this satellite need to be non-geostationary because it can go all the way to wherever they want it to be to record this image to capture this image of all around the Earth. And then for the purpose of GPS, okay, the purpose of GPS, and then the purpose of weather forecast, weather, okay, weather forecast, okay. While for this function, of course, they need this satellite to follow along wherever the country go. Why? Because whatever the telco that we have, if the country lose the satellite, then we will have no signal, This is why this signal this satellite needs to follow us all the way, wherever we go. MISAT, this is example of the name of the satellite lah. Example, misat. Misat. Okay, misat that we learn, the small one. Where is the misat? Where is the here it is. So this misat here is stationary. Stationary what? Geostationary satellite. Geostationary satellite. It will always follow the Earth. Okay, the other one, ISS, is non-geostationary satellite. We got the other one that is non-geostationary satellite, like Tiong-sat, Razak-sat, Pipit, ISS. And actually there are many more. So ours is Razak-sat. Ours is Razak-sat. Okay. You know what is, if something happen to this Razak-sat, then we will lose this opportunity. We will lose this GPS. Okay. Nowadays we travel in this Malaysia, we need this GPS, correct? Okay, if something wrong with this Razak-sat, then we will have this no signal of GPS. We don't know which way to go. Okay, you got the idea? And then we have nothing more. Okay, that's all. That's all. So you need to know what is similar and what is different. You memorize all of them. Oh, not far away. Escape velocity. What is escape velocity? What do you know about escape? You do know about velocity. What do you know about escape? Do you know escape? Press escape on keyboard. Escape. Something like that. Escape. We try to run away from something lah. V is the minimum velocity needed by an object on the surface of the Earth to overcome the gravitational force and escape to outer space. Do you understand this one? Do you understand this? You don't understand?
No.
So the idea is, we know that whatever is inside our orbit is being pulled by the Earth gravity, correct? Okay. If you want to go the opposite, we want to go the opposite way. Gravity go down. We want to resist it. We want to oppose it to go the other way. Against it. Okay. So what is the minimum velocity so we can pass through it? We can pass. We can overcome the gravity and eventually escape to outer space. If we below than this v, below than this minimum velocity v, then guess what? We will never be able to get out to space. Okay. That the gravity will pull us back to the Earth. Okay. It is like we kind of throw a rock. Okay, rock up there. Okay, against the gravity. But and then what? Suddenly, after certain height, the gravity win and pull the rock down back to the earth. Okay, and so that's their idea how to throw the rocket. How to throw the rocket up there so it can eventually overcome the gravitational and out to space. Okay, they're going to win. They're going to win the against the pull of gravitation. Okay, this is when they need to calculate. They need to know what is the minimum that we need to the motion that the speed that we need to go against gravity to surpass the gravitational force. If the distance of an object from the center of the earth is r, the mass of the object is m. Okay, and the mass of the earth is capital M, then the object possesses how to say it? So many s. The object possesses like that, gravitational potential energy. Gravitational potential energy, that is U. Okay, U stand for gravitational potential energy. Remember this one. Okay, and how to say it. Okay, stand for U, capital U. Okay, this time we got a new symbol for new physical quantities. Gravitational potential energy equal to negative GMM up there divided by R. Negative. Why negative? Soon we know. Figure below shows an object launched at escape velocity v. This object can overcome gravitational force and move an infinite distance from the Earth. Okay. Here it is. The object M can surpass the gravitational force and then out to surface. Okay. So yeah, we have learned this. Have you seen this formula? Have you seen this formula? Kinetic energy. Have you learned this formula? Kinetic energy. Where have we learned this kinetic energy? Have you learned this in sine form? Sine lower form.
Yes.
Yes. Oh, you have learned how to find kinetic energy lah. That belong to something that in motion that move. Okay. Okay, I need not to explain this more. So you take your prior knowledge from science lower form. Okay. If you forgot, then here it is to remind you back. To find kinetic energy, first you need to know kinetic energy belong to whatever the thing that is in move. If something move, then it got kinetic energy. The more the speed that it move, the higher the kinetic energy that it possess. If things doesn't move, then does it have kinetic energy? For things that doesn't move. Got no kinetic energy lah, correct? Okay. Kinetic energy, kinetic means refer to something that move. Do not move, no kinetic energy lah. Okay. Or this V here, if do not move, this V here becomes 0. The velocity, whatever multiply 0 is 0. Then kinetic energy is equal to 0. Okay. No kinetic, 0 stand for, 0 means no kinetic energy lah. Okay. So this time you need to take this back, okay, from your previous knowledge. Okay, take it out from your mind and put it there. Okay, because we're going to derive something new from the old formula that you learned. Okay, kinetic energy, a half multiply mv square, which is this m is referred to mass of whatever object that try to run away from the force. Okay, and this v refer to the speed of the object that want to run away lah. So again, this we have this formula, gravitational potential energy U. Okay. Escape velocity is achieved when the minimum kinetic energy of an object is able to overcome its gravitational potential energy. As such, this is when they try to combine those formula. Minimum kinetic energy plus gravitational potential energy equal to must equal 0. Okay, must equal 0. That is, we substitute the component of kinetic energy. Okay, plus we substitute the component to find gravitational potential energy. Okay, do not forget this negative here. Need to bring along. Must equal 0. Okay, this this I give to you lah. I give to you this because you are a mathematician. How you going to simplify all of them? See if you can combine them until you get the value, the subject of this that is V. I want you to simplify this and take this V to become subject. Means that the other component go to the right side. Okay, and then you'll start your algebra transfer until you get this. Still we don't want square, we only want V. And then also this square going to be square root. You're going to take to the right too. And at last we'll have this formula to find the escape, the minimum escape velocity. The higher than this is not a problem. Still you can, the higher the better lah. You can escape from the gravity force. Okay, this is the minimum. Okay, minimum that you need to move the speed before you can leave the earth. Okay, here it is the formula. We got two here. We got two. Before we got something similar to this, but got no two. We go back. The formula is to find the what? The speed of whatever orbit, whatever satellite orbit the planet. Okay, it is similar to this. But got no two. But in this case here we got two. So differentiate between them lah. So you might not interchange the formula when come to answer the whatever the question it is. Okay. Let use this new formula. Okay. So mass of the earth, we got this. Radius of the earth, we got this. We got this new formula that we derived. Okay, and then we fill all the information. Okay, G and M here is fixed. You can memorize it, the value, and R here is stand for what? This R here, capital R here stand for radius. Where is do we need to know the small r? We don't need to know. We don't need to know this small r here. We only need to know the length from the center to the surface only. Because in this formula, no need small r. We need bigger r. And then you do the calculation until we get the answer. So here it is, the minimum speed that you need before you can leave the earth. Leave the earth mean two things. First, you don't want to live anymore, and then you die, and then you leave the earth. This leave the earth is the other meaning. We go out to outer space, leaving the earth. Okay, the second meaning, the second meaning. Okay, not the first one. Okay, here it is. Can you imagine this? Can you be at this speed before you leave the earth? Do you understand this one? How speed it is? Can you imagine? You need to travel. You need to reach the distance 11 kilometer in 1 second. Oh, wow. 11 kilometer in 1 second, you know. Do you understand me? Okay, before that, we got this 400 kilometer from Berlin to KL. Okay, what time that will it take for you to transfer from Berlin to KL? That is 400 kilometer. If you can travel this speed, 11, let's say 10 kilometer per second. 10 kilometer per second. Okay, you're going to do like this lah. 10 kilometer per second. 10 to 400, multiply 40, correct? And so down there need to multiply the same, 40. Wow, you only take 40 seconds from Berlin to KL. Can you transfer this speed? Can you imagine how the rocket need to transfer to speed 40 kilometer per second? Okay, it is like from this, you know what? From our surface to the outer space, it only take about 400 kilometer, you know. So the idea, from surface, the rocket launch from surface until they reach to the outer space, they need to be only they need to travel. It will take only 40 seconds. 40 seconds under a minute, you know. Can you imagine that one? Rocket go up only 40 seconds before they can get out to the space. Okay, so yeah, we got something more. I'm going to finish this and upload the video. Okay, you're going to check all the video that I upload. Okay, for heat, you follow the link that I sent to you lah. Okay, we can skip this chapter because you learned already. Then we can go along with next chapter, chapter 5. Okay, Assalamualaikum. See you again. Oh yeah, before that, okay. Mana last hari tu? Sini. Jadi itulah dia cerita tentang escape velocity. Maknanya kamu nak escape, terlepas keluar daripada kita punya tarikan graviti. Jadi kita guna rumus ni lah. Kita guna rumus ni. Okay. So V here stand for escape velocity. Notice that we have 2. Inside we have 2. Okay. So in this case, in our planet, with our gravitational force, in order to escape our planet, at least what? At least if we can go from this surface to outer as fast as almost 10 kilometer 1 second, or you do whatever you want to do, as long as you can transfer from here to here, that it takes lower than 40 seconds, about 40 seconds, then means that you have enough speed. You have enough speed to escape. Okay, we'll have enough speed to escape from the force, gravitational force. That is the idea. Can you do that? Okay, can you create some? Can you create one transport that can travel that speed? Will you be able to create the transport? Okay, that is the idea when they create the rocket. So this so-called rocket, it can move with very high speed. So that is the purpose of the rocket. Escape velocity v of an object depends on the mass of the Earth, capital M, and distance r of the object from the center of the Earth. Escape velocity does not depend on mass of the object. Okay. Benefits and implications of escape velocity. High escape velocity of the Earth, that is almost 10 km per second, has benefits and implications on humans. One of the benefits is the Earth is able to maintain a layer of atmosphere around it. Do you understand this one? One of the benefits to the Earth, not is here typo maybe. Benefits to the Earth is able to maintain a layer of atmosphere around it. Do you understand this one? So the next detailed explanation for that is molecules in the atmosphere move at average linear speed of 5,000 meter per second. Okay, that is the speed of molecules in the air. It can move with 5,000 meter per second. Wow. So pretty quick. That is lower than the escape velocity from the Earth. As such, air molecules that are moving randomly will never be able to escape from the Earth into outer space. That is why. Okay, you understand? This molecule, we know that we can have high wind, move at very high speed. You know that. We got kind of like typhoon, like hurricane, and so whatever lah. Which this air move very very fast. But you know what? The fastest that it can move, the fastest that wind can move is only about this speed, 500 meter per second. Even so, this 500 meter per second is still lower than, it's still lower than this. Remember the condition that whatever thing that want to get away from, to get far from the Earth, to pass to outer space, at least they need this speed. So this explains why the air cannot escape. Because we don't want this atmosphere to escape to the outer space. Why? We will lose oxygen. Okay, we will lose oxygen. So here, atmosphere here is like this orbit here is like a storage for our air, cannot escape to the outside. High escape velocity of the Earth also enables commercial aircraft or fighter jets to fly to high levels in the atmosphere without the possibility of escaping into outer space. Commercial aircraft can fly at linear speed of 250 meter per second. Wow, not bad. If you're not familiar with this unit, then how about you turn this unit to kilometer per hour? Then you can compare with the speed of the car. Okay, see this speed in kilometer per hour, then you know how many times this airplane can go compared to car. Okay, I'm not going to show to you. You know already how to convert the unit. while fighter jets can achieve supersonic linear speed of up to 2,200 meter per second. Wow, so fast than commercial aircraft. So you can turn this to kilometer per hour, so you can compare this speed with the speed of car. Both their linear speeds are lower than the escape velocity from the Earth. Maybe some of you, or maybe all of you, have ever think, if rocket can go fly, why cannot aircraft or fighter jet go travel like rocket? You understand me? I believe you do think so. If rocket can go to outer space, why not fighter jet or aircraft? Cannot. If they try to reach the altitude, okay, and guess what? They will stuck there. They will stuck at this point. Okay, if they go, they accelerate now, very high. They accelerate until there. Guess what? They kinda is the highest that they can go. Before they falling back. Why? Because their speed is not exceed this speed. And then they cannot escape from this gravity. They try to do whatever they want to do to escape, but at last they cannot. Everything will start falling back if got not enough, if be in not enough speed. They will start falling back. But you know what? I got something interesting for you. This is what Allah has said in his book, Al-Quran, that whoever who want to test is it to test is it to know the greatness of Allah? How about we begin to try to get out from this atmosphere of our earth. Okay, and so such say Allah in Al-Quran, something like that lah. You can find the verse in Al-Quran. I don't know what verse it is. Where is it? Okay. Oh yeah. Since the rocket need to go with this speed, okay, so the other thing that you need to notice forward is the rocket, the body of the rocket going to collide, going to hit the air with this speed. That one we need to take in account too. Take in account. If I am I saying this right? Take to account, is it? Take to account. Mean we need to think about this too. So this is why they need to create the outer body of rocket which can resist the heat that coming from hitting the air with this speed. If the body of the rocket cannot withstand the heat, then what? Guess what? The rocket will get burnt and blow before it able to reach out to the outer space. So there are many things that we need to take to account. Moving along, now the launching of rockets requires large quantities of fuel to produce high in thrust that enables the rocket to achieve escape velocity of the Earth. Hence, it can send the spacecraft into outer space. Let me ask you something. You travel from this Baling to KL, which you know the distance is 400 kilometer. Okay, let's say you travel with your family of how many? Let's say five family members. Using what transport? A car. Okay, let's say a car you use to transfer from Baling to KL. Let me ask you this: how much petrol that you have to pay? So all of your you and your family can get there at Kuala Lumpur. How much do you think that you need to pay for gas, for petrol? It is about maybe, let's say it is about maybe 80. How about 80 ringgit? Correct? Around 80 ringgit lah. Okay. Now let me ask you the same question. Okay, instead of moving from Baling to KL, okay, in horizontal line, you are going to do the same. You're going to travel the same distance. Also, that takes 400 kilometer, but this time not in horizontal, but in vertical lines. Vertical, right up there to surface, go up straight forward, out, okay, out to the outer space. Also, that takes 400 kilometer, from this surface to this outer space is 400 kilometer, the same as Baling to KL. If Baling to KL, you have to spend 80 ringgit. Okay, 80 ringgit to bring 5 people only. So in this rocket, it can fill about 5 to 10% only. Let's say 5 to 5% only. 5%. But how much? How much they have to spend for fuel? How much? Is it 80 ringgit? The same amount of, the same number of people, 5%, but they need to pay how much fuel when we go travel upward? Million. Yeah, you heard me very clear. They have to pay million, million ringgit for fuel. For only one journey. Can you imagine that? So this is why I don't know Malaysia will never it kinda will never be able to afford this. Okay, to never be able to even have the knowledge to and skill to create the rocket. Solving problems involving escape velocity. You have calculated escape velocity from the Earth using this formula. In fact, this formula can also be used to calculate escape velocity from other bodies such as the moon, Mars, and the sun. Okay. Okay. If you want to try escape velocity for sun, you try it. Okay. Because you know the radius of the sun is the radius is way much um, uh, longest than way much longer than the radius of the earth. Then you try. Okay, try to calculate it. Okay, it's going to be how many times? How many times the speed? Wow. This is if you calculate this, then you come to know this is why whatever the satellite, whatever the ship that try to passing through, they can never get close to the sun. Let's say this is sun, they can never get close to the sun. They need to move move they cannot move so close to the sun, because it will the high gravity of the sun will pull whatever that passing close to it, and then guess what, you're going to need the engine which you can pull back the ship, which can surpass the escape velocity of the sun, which is there is no until now there is no engine that able to do that. They need to be really careful not to get close to the sun, the orbit of the sun. Escape velocity of Mars is low, therefore the gases are easier to escape to outer space. Okay, this caused the density of the atmosphere on Mars to be low, 100 times less dense than the Earth's atmosphere. Jupiter, on the other hand, has such a high escape velocity that hot gases on its surface cannot escape into outer space. Knowledge on escape velocity is important to determine how spacecraft can land and take off safely from a planet. Okay, we may be able to land on a planet, okay, but we will not be able to take off out of the planet. So be careful with it. If one day you become astronomer, you need to take this to account. Remember what the tips that I gave to you lah. Okay. Now we have come to example of question. Example 1, the moon and the sun are two bodies in the solar system. Table below shows the values of the mass and radius of the moon and the sun. Compare number 1, gravitational acceleration on the moon and the sun. Gravitational acceleration, what is the formula involved to find gravitational acceleration? Okay, what is it? G equal to what? G equal to what? What? As we used before. Where is it? Small g. Small g. Where is small g? Oh yeah, here it is. Okay. You need to use this formula lah to find G for Earth and G for what? Sun. Okay, where is it? Okay. G for moon. Sorry, G for moon and G for sun. We're going to use this formula to find gravitational acceleration. Okay. This one. Okay. And they fill the value lah. And then at last they get the G for moon and G for sun. So you see how much different is it? Sorry, how many different? How many difference are there? Oh, so many. How many times over than this? The gravity. Can you imagine this one? The gravity of sun is enormous. Okay, very huge. Second, find escape velocity v. Okay, from the moon and from the sun. So again, what is the formula for escape velocity? Okay, here it is. The formula for escape velocity. G and M here is the same. So G and M is the same because fix G and fix M. Oh no, this mass, this M here refer to what? Refer to the mass of the planet lah. Okay, refer to the mass of the planet. Okay, moon is this mass, sun is this mass. Okay, and then so you see here is to the power 30 more than to the power 22. So the idea, the mass of the sun is way much bigger than the mass of the moon. So this is what make this formula, whatever up there is become higher, and this will make the V also become higher. Okay, because this V and M here is at same level. They are on upper side. So if this M become higher, then this V also will become higher. The mass of the sun is higher than the mass of the moon. So this is why we will get escape velocity for sun is higher. So you see, escape velocity for the moon, okay, not so high, but escape velocity for sun, wow, to the power 5. To the power 5. Can you imagine this one? Let me convert this unit for you so you have a better imagination to compare. So we got 10 to the power 5. 1, 2, 3, 4, 5. Okay, so you see, here is 30. We got 30 for kilo. Okay, we turn to prefix kilo, and we got meter per second. Okay, per second. So this means that in order to get out from the sun, at least you need this speed. You can travel in 1 second. You can move to this distance, 618 kilometer. Can you do that in 1 second? Start from here, from this place, and then you, I don't know, you kind of run until 1 second later you have reached this distance. Can you do that? So this is why I told you nothing can escape from the sun. Okay, nothing can escape from the sun. Formative practice 3.3. Number 1, compare and contrast geostationary and non-geostationary satellites. Okay, you know. Okay, here it is. The comparison in the middle. Okay, compare, you give the whatever they both share the same characteristic, and contrast is only for their own. Okay, do not share with other. Okay. Where is it? What factors determine the linear speed of satellites orbiting the Earth? Okay, to answer this question, you to state the factor that which can determine linear speed of satellite orbiting Earth, you need to have this. You need to have this formula lah. Then we can look at the component inside. Then we surely know what the factors affect this linear speed. You understand me? Linear speed of satellites. Okay, linear speed. Linear. How to find? What is the formula to find linear speed? Here it is. To find the linear speed. Linear speed of satellite. So the idea is because G and M is constant, so we cannot state them, okay, to be the factor that can affect the speed, because they constant. The only thing that change is this R. Okay, this R. Okay, orbiting the Earth. Oh yeah, one other thing is the mass of the Earth. Okay, and so M here, sorry, the only thing that constant is this G, not this mass. Okay, so we got two factors that can affect the speed, the value of speed. That is the mass of the planet and the radius of the planet. So these two factors can affect the speed, linear speed. Number 3. State two factors which influence the value of escape velocity from a planet. Then we need this formula. Okay, here it is, the formula to escape. Then we need to look at the component inside to find the thing that can affect the V. So here it is, 2 constant, G also constant, and all thing that can change is only M and R. Okay, so the different the planet, different the value of M lah, correct? Different the mass lah. Okay, and will be also different for radius. Different planet, different radius lah. Okay. So the same, the two things two factors that can affect the escape velocity. Number 4, discuss whether escape velocity from the Earth for spacecraft X of mass this m and capital M is different from spacecraft Y of mass this. Okay, M2, My lah, let's say My, and this refer to Mx, Mx. Do you understand this one? Discuss whether escape velocity from the Earth, okay, means that both spacecraft is in the same planet, in the same planet. That is Earth, Earth. Remember that does this m, the mass for the object, got something to do with the escape velocity? Does the mass of the object which want to escape from the Earth, okay, want to do escape velocity, does that mass of object got something to do with escape velocity? If you see the formula here, can you see where is the variable of capital M? Is there variable of M, small m? No, it isn't. Means that the mass of the object which want to escape from the Earth, it is not important, you know. Either it is 150 kilo, either it is 2,000 kilo, either it is 10,000 kilogram. It doesn't matter. Okay, because we cannot find small m in this formula, which telling us that the mass of the things that want to escape doesn't influence this escape velocity. Okay, means that the escape velocity is the same for any object to escape from the planet. It's all the same, no matter what the mass is. Number 5, Proba 1 satellite orbits the Earth at a height of 700 kilometer. Okay, what is the linear speed of this satellite? What is the linear speed v of this satellite? Okay, so what formula to find the speed of the moving satellite orbits the Earth is the same one, is this. Okay, you're going to use this, okay, to find the speed, linear speed of the whatever satellite orbiting the Earth or whatever it is. If the satellite orbit the Earth, then m here you put the m of Earth lah. If the satellite orbit the planet, the other planet, let's say planet of Sun, then m here you must put the mass for Sun lah. Okay, I'm not going to calculate that. You are the one who going to find the final answer. So now we have finished all the chapters, all the chapter 3. Okay, we finished all chapter 3, and I also assume that you finish all chapter 4 too. Okay, do you watch the movie that I sent to you? Do you? Yeah, you should. Okay. So I assume that we also done chapter 4 lah. Okay. Got no problem chapter 4 everyone? Are you happy about it? Chapter 4. It is about heat It is about heat. Now let's go to chapter 5, okay? Chapter 5. The title is waves. Okay, waves not wives. Okay, wives is different. Okay, this is waves. Okay, 5.1. Sorry. Let me start over the camera